Okay, now this sounds good. So what I wanted to share with you is some work that is Rebecca and I, along with Nor White, Mike's former student, and Rob Drumfield, and some students in Rebecca's and Rob's lab on expanding Manakin phylogeny. So I'm going to do a little bit of a review of some ultra-conserved element phylogeny material that was covered by Rebecca at the Panama meeting that's currently in review at Molecular Phylogenetics and Evolution. And I'm going to tell you about some of the stuff we've started since then. If we think of avian phylogenomics, there are really two big approaches. One is, and here I'm thinking at deeper levels. Obviously, the RAD-seq is wonderful at relatively close levels, and unfortunately, Rick and Jake have added a number of species that aren't in these trees. But you know, I'm now mad at you. But at deeper levels, ultra-conserved element sequence capture or sequence capture of exons, as Rick and Jake and others did in their paper of a few years ago, are great methods because they reduce the size of the genome. Many of the ultra-conserved elements we're using overlap with the ultra-conserved non-coding elements that Morgan analyzed. The difference here is we don't really care about the function. The ultra-conserved portion simply represents a handle that allows us to pull this segment of DNA out of the genome, and most of the variation we're looking at is flanking variation, which is hopefully neutral. Possibly not, but hopefully. It's inexpensive. We can use low quality tissues. We routinely use topad tissues in the lab. Data types are limited, and it's limited to a few thousand loci, which, for somebody who's now been doing phylogenetics since the late 90s, yeah, that's great. The other way you can go is whole genome sequencing, which could range from low coverage genomics, which is what I'm really going to talk to high coverage, high coverage using many technologies like the platinum scale, platinum quality genome of Carxithia. You can obviously extract multiple data types. You can get very large data sets, even hundreds of megabases. It's more expensive, and the analyses are more computationally demanding. So let's start out with the ultra-conserved elements, and these slides are going to be up. Betty's going to post them, so I'm not going to belabor all of this. For this analysis, we used the tetrapod 2.5K probe set, so we're targeting about 2,500 ultra-conserved elements. Most nodes have strong support. So I would say that to the extent we believe analyses of the data set of this size, we've largely covered the backbone of mannequins, and we have now a good phylogeny, which I know Rebecca has shared with some of you for other downstream analyses. And as I said, this is in review and will hopefully, knock on wood, be out soon. A few problem nodes do remain, and I'm highlighting some of the problematic clades. In two cases, we do have non-monophyletic genera. One is relatively trivial and has been known for a while, which is this Neopelma tyrannudes non-monophylean. That's easy enough to deal with. We just need a new name. Systematists love naming things, so cool. and Cardsiphia antilophia, where we actually, in principle, antilophia could be sister to the Cardsiphia clade, or nested within. Nested within is the optimal solution in most analyses. But I want to stress that the support here is somewhat lower. And you can see other clades where we have at least more limited support despite the large size of this data set. And I'm going to just emphasize the instability of Cardsiphia antilophia by showing that it is unstable to different analyses. We have up here concatenated analysis, which is relatively standard. SVD quartets is a method that has some interesting properties and should be consistent given the multi-species coalescent. And Astral is a gene tree summary method, which, if you make certain assumptions, should be consistent, i.e. converge on the true topology in expectation under the multi-species coalescent. Across the top are some different data filtering schemes, which I won't go into. Big point I want you to take away from this is we get a bunch of different trees, often with limited support. Okay, so what can we do to improve this? More data, and specifically whole genome data. I'm going to give a benefit of many data types. This is something out of a paper Rebecca and Sushma Reddy and Mike was on this, Nor was on this, a number of other folks, showing that if we look at the base of neo-AVs, and this is a tree of trees. In other words, I'm clustering the distances among trees. So if we look at the base of neo-AVs and focus on trees generated with coding data, they form a cluster. If we look at non-coding data, we see a second cluster, and these are relatively rarely accumulating changes to the genome, transposable element insertions or insertions and deletions as a whole. So depending on the data type you look at, you get subtly different trees. These trees are extremely similar. But there are still some subtle differences, and they are linked to issues of the type of data we analyze and presumably the models we're using to analyze them. So I would say that's a benefit of looking at the whole genome, is we're not limiting ourselves to one particular data type. So long-term goal, we wanted to use low coverage whole genome sequencing to resolve 2 genera. Can we actually increase support? Maybe it's a phylogeny, or maybe it's a mess due to gene flow and or hybrid speciation. So those are caveats. Approach, we produced 1 library per taxon, generated sequence using a HiSeq X. We then mapped reads to a reference. Now, usually we think of read mapping as within species. Here, what we did was something, I think, a little more daring, potentially maybe too daring, I don't know. We mapped the reads to a reference from a different species. In all cases, we used the available Neopelma genome, because we wanted to map onto something that was equally different from all of our samples. In other words, we didn't want to bias by having, closer and more distant relationships. Then we generated variant call files and converted these to consensus sequences. And the pipeline we're using, we're still tweaking a little bit, but we'd be happy once it's done to supply, we'll put it up on GitHub or something. Here's the first question: how much sequence data can we recover from each taxon? And for this, I extracted over 4,500 UCEs plus 1 kilobase flanking. out of Neopelma. That's over 10 megabases, and it's mostly non-coding. I supplemented this for one of the points was a comparison between recovery from coding regions and non-coding regions. So the Promedal paper from 2015, I just took the 259 regions. That is obviously smaller, but it's a great representative coding data set. And remember, the point here is not the amount of data total at this point. It's a question of how much can we map to these sequences. So I felt, this was fine. And the answer is we can much more successfully map to the coding regions. Obviously, as we get more coverage, so down at the bottom we had only about 8-fold coverage. Some of our better sequencing libraries, we got almost 20-fold coverage. We can map much more successfully to the coding regions than to the, to the coding regions than to the non-coding regions. So this is, as these numbers go up, we're getting more and more unresolved bases in the sequences. So coding has some real benefits. However, the recovery is extremely well correlated. So although the slope of a line for how much sort of unresolved data is less than a 1-to-1, as you would expect from this, we get very strong correlation. So for example, we see back here, I should have looked up what this bad library was. Apparently high coverage, but poor mapping. But the point is it's correlated between the two of them. It's just shifting the line. Okay, what can we do with this? As a preliminary phylogeny, we generated an astral tree. I also have concatenated trees from this that I'm really not going to go into. First, let's just take the coding regions. Now, this is a little bit of an unfair comparison. The big thing I want you to take away from this is the efficiency of the mapping, not the details of the phylogeny. I could pull out more coding regions. I could even use some of the phylogenetic informativeness criteria on those. And I'm sure I would get a better tree in terms of support. However, we still, in these with only 259 loci, get some low support. The topology in Chirixifia antilophia is not one we recovered in the UCE paper. However, as I said, support is low. Antilophia is still nested within. Let's now go to the larger non-coding data set. And as I said, this is very preliminary. This topology is identical to our largest data set astral tree from the submitted paper. All nodes in here have posterior probabilities of 1.0. If you like to put numbers on your trees. The topology is identical to the concatenated tree out of IQ tree. So concatenated and astral are identical. So I think we're closing in. I would still like to expand the coding data set and see whether there are any issues with data type. But I think we're closing in on a reasonable phylogeny. Now, one thing I want you to take a gander at is how short these branches are. This was a fairly rapid radiation, and possibly we have some gene flow on taxa confusing us. So let's see. Conclusions. we could get a fair amount of data. Even our worst library, which unfortunately is for one of our favorite taxa, Antilophia, only 7.4 megabases. But I say this as only 7.4 megabases when I started phylogenetics. 1 kilobase was like, okay, cool. And I'm not that old. And obviously we do get better recovery using the coding data, which is actually good if what you want to do is analyze coding regions. The big thing I want you to big reason I wanted to bring this to the Manakin RCN group, of course, is that these are a resource for the Manakin community. And I initially, since I had those trees with our new genomes on them, figured, oh, well, everybody can get the identities of the taxa off of that when they download from Betty. But at the last minute, literally at the last minute, after I uploaded and gave this to Betty, I added a slide where, at Rebecca's urging, where we mapped out the new genomes. Red arrows indicate genomes for which high quality sequences, what Morgan is calling draft quality. Those are pretty darn good genomes. Many are made with multiple technologies. The Neopelma genome is actually a phased diploid genome. So, in other words, for many things, you actually have 2 separated alleles. That's pretty darn good. Yeah, maybe they're not perfect, but they're good. The newer genomes are indicated in purple. We actually have, in addition to the high-quality Lepidothrix coronata genome, we have 2 additional ones from the exquisita and minuscula subspecies, minuscula being from the northwest. I would say likely to be a different species. But, you know, and of course these are sort of the different green morph. Did I flip when I said the species? Minuscula northwest. This is a green morph and a black. So we have some color polymorphisms there. So as a resource, what are we doing? Well, Nor is working on visual system genes, and she's actually comparing a lot of this to probes. She has a probe array that can pull out these visual system genes, so we're looking at the accuracy of our sequencing. Students in Rob's and Rebecca's group are interested in looking at plumage-related genes. I'm interested in mitonuclear coevolution. Since Nor is really, this is the focus of her postdoc, you know, if you're interested in visual system genes, she's really taking this on as her core project. So I don't think she's looking for collaborators. These just talk to us, or if you want to use it for other things. And with that, I'd just like to thank the folks that gave us money and the group. And I don't know how much time I have for questions.